Hello, welcome back to Elements of Civil Engineering and Mechanics class. Today what I am going to do is I am going to cover composition of coplanar non-concurrent force system. For that, first we have to prove Varignon's theorem of moments. So what is the statement first of all? Statement says that algebraic sum of moments of a coplanar force system about a point in the plane is equal to the resultant of the forces is equal to the moment of the resultant. So it states that algebraic sum of moments of a coplanar force system about a point in the plane is equal to the moment of the resultant about the same point. Proof. So what I do is I am going to consider a system of forces. This is x-axis, this is y-axis. So let me consider a system of forces. Okay, I am going to call this P, Q, S, etc. And this is the point O at which the forces are acting, and these forces are coplanar. So for these forces, let R be the resultant and let R make an angle of theta. That is, let theta be the angle made by the resultant with respect to the horizontal axis. So what I do is I am going to take this resultant, same point, so same axis, I am going to separate the resultant. So this is the resultant R, this is theta, okay, and if I take the horizontal component of the resultant, so I am going to call that as Rx, that is equal to R cos theta, and the vertical component of the resultant is Ry, that is same as R sin theta. Or sin theta. So the resultant forces, the component forces will be acting like this. This is for the resultant. Along the same line, if theta 1 is the angle made by the force P with respect to the horizontal, if I draw that separately, x, y, and this is P, this is theta 1, and the horizontal component is, if I call Px equal to P cos theta 1, similarly vertical component is Py equal to P sin theta 1. Okay. So, to start with, what I do is, I am going to take a point B here along the y-axis. So, you can take this point anywhere in the same plane. Just for my convenience, what I do is, I am going to pick a point here along the y-axis and I am going to call that as, say, B. So, from B, I am going to draw a perpendicular to the resultant, and I am going to call this point as B dash. B dash is the point where the perpendicular meets the line of action of the force resultant, Okay. So, if this is theta, if I consider this triangle, that is OBB dash triangle, so this is 90 minus of theta, and of course this is 90 degree. So, in this triangle, if this is 90 degree, if this is 90 minus theta, so this should be 90 minus of 90 minus theta, that should be equal to theta. So, this is angle theta. So, what I do is, to start with, I am going to take the moment of the force R about the point B. So, what I do is, I am going to take the moment of the resultant about the point B. Now, let us consider a system of forces P, Q, S, etc. acting at point O. Let R be the resultant, let R be the resultant of those forces. So, let theta be the angle made by the resultant with respect to the horizontal. Let us consider a point B. Along y-axis, From the point B, Draw BB dash perpendicular to the line of action of the resultant R from triangle OBB dash, angle OBB dash equal to theta. So, moment of the resultant about the point B equal to the force R and the perpendicular distance is BB dash. So, I am going to take this BB dash as small d, that is R multiplied by d. Okay. Let me call this as equation 1. So, next what I do is, if you look here, if you look at this figure, so Rx equal to R cos theta and Ry equal to R sin theta. So, if I call this as figure 1 and this as figure 2 and this as figure 3. Here, if you look here, R multiplied by D is the the moment of the resultant about the same point. Along the same line, what I do is, for this force P, I am going to extend the line of action of this force from this point B. I am going to draw a perpendicular to this. So, I am going to call this as B double dash. If this is theta 1, this should be theta 1 as well. Okay. So, along the same line, moment, similarly, moment of the force P, about the same point B is given by, it is P D1 I am going to call, where P D1 is this perpendicular distance, that is equal to P D1 multiplied by P D1 multiplied by 3, that is, I am going to call this as, yes, moment is P D1, that is equal to, what is D1 by the way? D1 equal to OB cos theta, that is equal to OB cos theta. So, I am going to take this PD1 OB cos theta, and another thing here, I am going to make little bit of correction, RD equal to, so D is nothing but OB cos theta, RD equal to OB OB cos theta with R that is equal to OB multiplied by R cos theta, that is nothing but OB into Rx. So this I am going to call as equation 1. Okay. So along the same line, so moment of the force P about the same point B. So by following this, what I can do is I can write PD1 equal to OB into Px. Okay. Similarly, for if I take the force Q, okay, which is at a distance, perpendicular distance of d2 from the same point B, I can write Q d2 equal to OB multiplied by Qx, and if I take the force S, d3 is the perpendicular distance and OB multiplied by Sx. Okay. So I am going to call this as equation A, call this as equation B, and I am going to call this as equation C. If I have other forces, more than 3 forces, so I can write like this. Okay. By summing all the above forces, we get PD1 plus QD2 plus SD3 plus etc. that is equal to OB is the common, I am going to take Px plus Qx plus Sx plus etc. Okay. So what is Px plus Qx plus Sx? That is nothing but Rx. See, this is the sum of algebraic sum of the horizontal components of all the individual forces that should be equated to the horizontal component of the resultant. So for this I can write OB multiplied by Rx, OB multiplied by Rx. So this is PD1 plus QD2 plus SD3 plus etc. that is equal to this. So I am going to call this equation 2. So compare these two equations. So I can equate equation 1 and equation 2. Look here, OB multiplied by Rx. This is also OB multiplied by Rx. So I can equate RD with this. By equating equation 1 and equation 2, we get RD equal to PD1 plus QD2 plus SD3 plus etc. Hence, it is proved. What is this? This is the moment of the force P about the point B. This is the moment of the force Q about the same point B, and this is the moment of the resultant about the same point B. So what it means? in a coplanar force system here, so moment of the resultant about a point is equal to the algebraic sum of moments of all the forces, all the individual forces in the same plane about the same point B. I hope this is clear. So let us solve a problem on this. So problems. A rigid plate ABCD. A rigid plate ABCD is subjected to forces as shown in figure. As shown in figure. Compute the magnitude direction and line of action of the resultant of the system with reference to point A. Okay, let us go through the problem first. The problem says a rigid plate ABCD is subjected to forces as shown in figure. Compute the magnitude, direction and line of action of the resultant of the system with reference to point A. Okay, that's what the problem says. So what it means is, if you look at the forces, we have four forces acting in each edge or in each corner of that square plate. So the dimension of the plate is 1 meter by 1 meter. At point A there is a load of 100 kilonewton acting downwards. So this is 200 kilonewton, again this is 100 kilonewton horizontal. So this is 200 kilonewton at an angle of 30 degree with respect to the horizontal. So this is a system of coplanar non-concurrent force. So why it is non-concurrent? Of course coplanars, they are all acting in the same plane. Non-concurrent because if you extend these forces, those forces don't meet at a single point. All these forces. Say for example, if I take this force, if I extend the line of action of the force backwards, and this force meet at this point, and again if I extend this back, yes, these three forces meet at this point. But if I take this force, if you extend this way and this way any longer, okay, this line is not going to meet at this point at any cost. So even one case happens like that, then it is non-concurrent force system. Okay, that means all the forces are not acting at a single point. Even if I take this force, yes, this force is acting here. Okay, so no other forces are able to meet this force. But if I take this force, yes, if I take this force, extend the line of action of this force, so these two forces meet at this point and this is meeting at that point. So one is out. So to start with, what I should do is, first I need to resolve the forces in the horizontal and vertical directions to solve the problem. So what I do is, I am going to draw another figure ABCD, and if I take this force 100 kilonewton at point A, of course I don't have to resolve this force because it is already vertical and it does not have a horizontal component. So if I take this force, if I take the force at B, which is acting at an angle of 45 degree with respect to the horizontal, so I can resolve this force into its components. So horizontal component is, so it is 200 cos 45, vertical component is 200 sin 45. So it is 200 cos 45 and the vertical component is 200 sin 45. And if I take this 100 kilonewton, already horizontal, we don't have to worry about resolving it. So if I take this force, yes, this will have a horizontal component and this will have a vertical component. It is 200 sin 30 is the vertical component acting upwards and the horizontal component is 200 cos 30 acting towards right. Okay. Of course, this is A, this is B, this is C and this is D. To start with, what I do is, I am going to find out the magnitude and direction. Later on, I am going to find out the line of action of the force. In case of coplanar concurrent force system, you only calculated the resultant, that is the magnitude of the resultant, and the direction of the resultant. Direction means the angle at which it is acting with respect to certain reference line. Is it not? But here, because it is non-concurrent, not only that direction and the magnitude, and also we need to locate the position of the resultant. So that resultant may be acting with reference to A, may be acting here, 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 or here, here. We don't know where exactly it acts. So we need to find out. So here we need to find out three quantities: the resultant value and the angle the resultant is acting with reference to some reference line, and the position of the resultant. So to start with, I am going to compute the magnitude and direction. Afterwards, I go for line of action. So this is to compute the magnitude and direction. So now algebraic sum of the components of all the forces in the x direction, I am going to call that as sigma fx, that is equal to sigma fx equal to, so let us take all the horizontal forces starting from here. At A, is there any horizontal force? No horizontal force. We don't have to worry about it. Here, yes, there is an horizontal component which is 100 cos 45 and it is acting to the left. So I am going to take minus 200 cos 45. Here, if I come to C, yes, there is a force 100 kilonewton acting towards right, that is plus 100 kilonewton. Okay, 100 kilonewton. Next, if I come to point D, 200 cos 30, it is acting towards right, 200 cos 30, that is plus. So after solving this, so we are going to get sigma fx equal to 131.78 plus 131.78 kilonewton. See, if I get 131.78 kilonewton with plus sign, it means this resultant force in the horizontal direction should be acting towards right. That is 131.8 kilonewton. This is acting towards right. Sigma fx. And sigma fy equal to, yes, we will consider all the vertical forces. If I come to point A, there is a force 100 kilonewton acting downwards, so that's why it is minus 200 sin 45 acting downwards, minus if I come here, there is no vertical force, and if I come here, there is a vertical force acting upwards, that is plus 200 sin 30. So sigma fy equal to, the answer is minus 141.42 kilonewton. Minus 141.42 kilonewton. When I get minus, so how this force should be acting? It should be acting downwards. So that is sigma fy equal to 141.42 kilonewton. Okay, so it is acting downwards, and the resultant R equal to square root of sigma fx square plus sigma fy square, that is equal to square root of 131.8 plus sigma fy. See, we must take this value, not this value. Okay, that is 141.42 So of course numerically it does not make any difference, 193.3 kilonewton. That is the resultant. So if I show this in a figure, sigma fx acting horizontally towards right, that is sigma fx, that is equal to 131.8 kilonewton, and sigma fy is 141 equal to 141.42 kilonewton. It is acting downwards, and this is a rectangle. Okay, when I join the diagonals, when I join the corner points, this is the diagonal, this is the resultant R. Then what is the resultant? That is equal to square root of sigma fx square plus sigma fy square. So that is 193.3 kilonewton, or equal to 193.3 kilonewton. Okay. Then I need to know at what angle this resultant is inclined with reference to some reference line. Here, as usual, we always take the horizontal line as reference. So I am going to call this as theta. Therefore, and tan theta equal to opposite side, that is sigma fy divided by sigma fx equal to sigma fy is 141.42 and sigma fx is 131.8. Therefore, angle theta equal to 47.02 degree. 47.02 degree. Okay. So theta equal to 47.02 degree. Okay. So we calculated what is the magnitude of the resultant, which is 193.3 kilonewton, and the direction of the resultant, that is at an angle of 47 degree with respect to the horizontal. The next thing is we need to find out where is the position of the neutral axis, where is the position of the resultant, that is with respect to point A. We need to find out with respect to point A. Okay, the value changes as we take different reference points, but the position remains constant. Say for example, this resultant is acting somewhere here. Okay, we are going to get the distance of the resultant. If you find out with respect to A, we are going to get that value. So if you try to find out with respect to B, you are going to get a different value. As far as the position of the resultant is concerned, it remains there where it is. It is constant. So let us find out where exactly the location of the resultant or the position of the resultant. So if you look here, line of action of the resultant, we need to find out. Line of action of the resultant is nothing but the position of the resultant. To find out the position of the resultant with respect to point A. To find out the position of the resultant with respect to the point A. So for that, what I do is I am going to take moments of all the forces about the point A first. and add them algebraically. So by taking moments of all the forces about the point A and adding them algebraically, we get, I'm going to call this as sigma MA, because I am taking the moments of all the forces with respect to point A. So if I come here, yes, there is a force 100 kilonewton. So moment of this force about this point is 0, because the line of action of this force is passing through A. Just to make it clear, if I take a force here, say F, if I take a point A here, what is the, and if D is the distance, that is the perpendicular distance of this force from A, then moment of this force about point A is given by F multiplied by D. Is it not? Of course it is counterclockwise with minus sign. Okay. So force multiplied by D. What if I reduce the distance D? That means I am shifting this force upwards. Then what happens to F multiplied by D? It reduces. If I reduce the value of D further, again the moment reduces. Finally, if I bring this force exactly along the line of A, then what happens to D value? It becomes 0. Once D becomes 0, the moment automatically becomes 0. That means moment of any force about a point which is located on the line of action of the force is always 0. Here I am considering this point, and if I extend this force, and this force line of action has point A on it, so the perpendicular distance is 0, so the moment is 0. So that is 100 kilonewton multiplied by 0. 100 kilonewton multiplied by 0. Next, if I take 200 sin 45, okay, 200 sin 45, again extend the line of action of the force. So you can extend the line of action of this force this way and upwards any longer, even for a kilometer you can extend that line of action of the force. So if you extend this line, so again this line of action of the force has point A on it. That is, the point A falls exactly on the line of action of this force as well. If that is the case, what is the perpendicular distance? It is 0. So it is 0. So whether it is plus or minus, it doesn't matter. So next I am going to go to this force. So this is the line of action of this force. So this cannot be 0, because from point A, if you draw a perpendicular line, there is a distance, that is 1 meter distance. And this force is causing counterclockwise or anti-clockwise moment about the point A. And this gives out some value, that is 200 cos 45 multiplied by this perpendicular distance, which is 1 meter. Of course this is 1 meter and this is 1 meter as well. So I need to consider this 1 meter. And what is the kind of moment this force is causing about A? in which direction, whether it is clockwise direction or anti-clockwise direction. For that, what you need to do is, you have to imagine a thread of length 1 meter, that is this distance, and because you are trying to find out the moment of this force about this point, keep one end of the thread here and take the other end of the thread which ends here and move in the direction of the arrow. Then this traces an anti-clockwise motion, is it not? So according to our sign convention, any anti-clockwise moment is negative or minus. So that is 200 cos 45 is the horizontal force into 1 meter is the distance, with minus sign because it is anti-clockwise. So we have covered this force and this force. Again, if you come to point C, we have 100 kilonewton force. So extend this backwards. This is the line of action of 100 kilonewton. So from this point, draw a perpendicular line to the line of action of 100 kilonewton. So what is the perpendicular distance? Again, it is 1 meter. Okay, what is the moment this force is causing about this point? For a moment, what you can do is, you can imagine that this arrow end has been shifted to this point. That means you will see that arrow here. That can be done. So this 100 kilonewton causing a clockwise moment about A. So 100 kilonewton multiplied by 1 meter perpendicular distance, 100 kilonewton, 1 meter perpendicular distance, plus sign because it is causing clockwise moment. Okay. So this is covered. Next, coming to the point D, we have two forces. I am going to take this force, 200 multiplied by sine 30. So what is the perpendicular distance to the line of action of this force from point A? This is the perpendicular for this force. Okay. So what is this distance? 1 meter. So 200 sine 30 multiplied by 1 meter is the moment this force causes about the point A. And what is the sense? It causes anti-clockwise moment. The force causes anti-clockwise moment about the point A. According to our sign convention, any anti-clockwise moment is always negative. So whenever you multiply a force by a distance, it becomes a moment. Then you must think in terms of clockwise or anti-clockwise. Just because this force is acting upwards, you should not take that as positive. No, it is not. We are not talking about the force. Instead, we are talking about the moment. Okay. Again, I am repeating. Whenever we multiply a force by a distance, that becomes moment. When you think, you must think in terms of clockwise or anti-clockwise. So coming back to this, 200 sine 30 multiplied by 1 causing anti-clockwise moment about the point A, plus 200 sine 30 multiplied by 1 with minus sign. Next, there is a horizontal component of 200 kilonewton force. Again, the line of action of this force is passing through the point A. So automatically this force does not cause moment about A. So that's why 200 cos 30 is the force, multiplied by 0 is the distance. That is 200 cos 30 multiplied by 0. It doesn't matter whether you put plus or minus. So finally, sigma MA equal to minus 141.42 kilonewton, minus 141.42 kilonewton meter. That is the moment experienced by the point A due to all these forces. What is the kind of moment? Because it is a minus sign, sigma MA is anti-clockwise, 141.42 kilonewton meter. In the anti-clockwise direction. Because I got this value is negative. That means the resulting moment is causing anti-clockwise rotation. Okay, I am going to call this as equation 1. See, coming back to the resultant R, which we found out the value and the angle. I need to know the position of the resultant, where exactly that resultant falls with respect to point A. If I put that resultant on this side, that is on the right side of A, like this, I know the resultant is acting like this. If you remember, if you look back at the previous figure which I wiped out just now, the resultant is like this, acting. If I move this resultant on this side, if I take the moment of the resultant about point A, that causes clockwise moment. Okay, but what is the resulting moment? Anti-clockwise. So we cannot place that resultant on this side. If I put the resultant on this side, so that resultant causes anti-clockwise moment about the point A. Then the resultant falls somewhere along this line. Okay? The magnitude of the resultant is 193.8. And the angle the resultant makes with respect to the horizontal is 47.02 degree. 47.02 degree. Okay. But I need to know at what distance this resultant is located with respect to the point A. I am going to call this as, say, distance D. I need to know what is this distance. Then only I can fix the position of the resultant. Okay. Now what I do is I am going to take the moment of this resultant about the point A. Let R be the distance of the resultant, let small d be the distance of the resultant with respect to the point A as shown. As shown. So moment of the resultant equal to resulting force multiplied by D with minus sign, because it is causing anti-clockwise moment about the point A. So that is minus 193.8 D kilonewton meter is the moment. That is nothing but 193.8 D is the moment. Once I take out minus sign, I can replace that with anti-clockwise direction. I am going to call this as equation 2. We know algebraic sum of moments of all the forces about a point is equal to the moment of the resultant about the same point. So if you look here, these two can be equated without putting plus or minus, because this is counterclockwise, this is also counterclockwise. We fix the position, that is on which side the resultant falls, by applying logic, by looking at this value. Okay, now I can equate equation 1 and 2 by equating equation 1 and equation 2. We get 193.8 D, that is equal to 141.42. Of course, the unit of this is kilonewton meter. Therefore, D equal to, the value of D equal to 0.73 meter. So finally, you express the answer, you write a figure. This is point A, okay, and this is the resultant of magnitude 193.8 kilonewton, and this resultant makes an angle of 47.02 degree with respect to the horizontal, and the resultant is located at a distance of D which is equal to 0.73 meter from A, because the problem says find out the magnitude, direction and the position of the resultant with respect to A, and we found out the position of the resultant, which is 0.73 meter with respect to the point A. This should be your final answer. Put this in a big rectangle. This completes the problem. Thank you for the class.